Mars, often described as a disappointing hellhole, lacking the essentials for human survival, has the potential to become a habitable planet through the process of terraforming. While it may seem like a science fiction tale, terraforming Mars is indeed a possibility. However, achieving this transformation requires a comprehensive understanding of the planet's challenges and the implementation of innovative solutions. In this article, we will explore the process of terraforming Mars, from creating a suitable atmosphere to establishing a thriving biosphere and addressing long-term challenges. Challenge 1. The atmosphere. Mars currently possesses a thin atmosphere, devoid of the necessary elements to support life as we know it. To terraform Mars, we need to provide it with an Earth-like atmosphere consisting of 21% oxygen, 79% nitrogen, and a small amount of CO2, with an average temperature of 14 dec and a pressure of 1 bar. However, Mars lacks the required oxygen and nitrogen, and its atmosphere is too thin to sustain life or protect from radiation. To address this challenge, we can utilize powerful lasers to melt Mars' surface, releasing gases such as oxygen and carbon dioxide that are trapped within the rocks. By deploying an array of mirrors in space and focusing sunlight onto Mars, we can effectively melt the surface and initiate the release of these gases. This process, known as thermolysis, can be facilitated by solar-pumped lasers, which absorb energy and emit laser beams. As the lasers heat the surface, significant amounts of oxygen and carbon dioxide emerge, contributing to the creation of a more substantial atmosphere. The melting process, accompanied by intense lava flows and volcanic activity, would generate storms and ash, leading to the rise of hot steam and the formation of shallow oceans. However, further refinement and adjustments would be necessary to achieve the desired composition and stability of the Martian atmosphere. Challenge 2. Biosphere. Establishing a biosphere on Mars presents another formidable challenge. The introduction of life forms, both in the oceans and on land, requires careful planning to prevent destabilization and ecosystem collapse. The process begins with seeding the young Martian oceans with phytoplankton, which would serve as the foundation of an aquatic food chain. Subsequently, zooplankton, fish, and eventually more complex organisms could be introduced, leading to a thriving marine ecosystem. On land, the laser technology used in the terraforming process can be leveraged to break down the surface into smaller fragments, creating a dark mud-like substance. This mud can serve as a suitable medium for the growth of fungi and nitrogen-fixing bacteria, which would enrich the soil with nutrients and pave the way for the introduction of plants. Initially, plants native to volcanic islands on Earth would be well suited to the Martian landscape. Over time, these plants would facilitate the establishment of grasslands and forests, forming a self-sustaining ecosystem capable of supporting diverse plant and animal life. However, maintaining balance within the Martian biosphere is crucial. The introduction of additional species must be carefully managed to prevent overgrowth, depletion of resources, or the extinction of key species. Without the same level of biodiversity found on Earth, the Martian biosphere is more susceptible to disruptions, making long-term monitoring and intervention necessary to ensure its stability and sustainability. Challenge 3. The long-term future, establishing sustainable infrastructure on Mars. In addition to the creation of an artificial magnetic field to protect Mars from solar radiation and cosmic rays, the long-term future of Mars colonization and terraforming requires the establishment of sustainable infrastructure to support human life and ensure the viability of the planet as a habitable environment. This entails several key challenges and areas of development. Energy generation and distribution. To sustain a terraformed Mars and support a growing population, a reliable and efficient energy infrastructure is crucial. While nuclear facilities may initially provide power for the magnetic umbrella and other essential systems, it is essential to develop alternative and sustainable energy sources. This could include harnessing solar power through advanced photovoltaic systems, or even exploring the potential of utilizing geothermal energy on Mars. Efficient energy distribution networks will be necessary to deliver power to various settlements and resource extraction sites across the planet. Water and resource management. Ensuring a steady supply of water and managing essential resources are vital for the long-term survival of Martian colonies. While significant efforts have been made to extract and utilize subsurface water ice, sustainable water management systems must be established to recycle and conserve this precious resource. Additionally, efficient resource management strategies, such as mining and processing Martian regolith for essential elements and minerals, will be necessary to support ongoing construction, manufacturing, and agriculture on Mars. Agriculture and food production. Establishing sustainable agriculture and food production systems on Mars is crucial for achieving long-term self-sufficiency. Advanced greenhouse technologies and hydroponic systems will be essential to cultivate crops in controlled environments. Additionally, research and development efforts must focus on genetically modified crops and innovative farming techniques that are well adapted to Mars' unique environmental conditions, including lower gravity, reduced sunlight, and different soil composition. Habitats and infrastructure. As the Martian population grows, the need for durable and efficient habitats will increase. Innovative construction methods, such as 3D printing using local Martian resources, can significantly expedite the construction of habitats and infrastructure. These structures should provide protection from radiation, maintain a controlled atmosphere, and offer comfortable living conditions for long-duration stays. Moreover, the development of transportation networks, including rovers, tunnels, and aerial vehicles, will facilitate inter-settlement connectivity and resource exploration. Environmental stewardship and conservation. Preserving and protecting the Martian environment is crucial to maintaining the long-term sustainability of the planet. Strict regulations and protocols must be implemented to prevent contamination, safeguarding the integrity of Mars' delicate ecosystems. Environmental monitoring systems, including sensors and remote sensing technologies, will play a vital role in assessing the impact of human activities and ensuring responsible resource extraction and waste management practices. Interplanetary collaboration. The long-term future of Mars colonization and terraforming necessitates international collaboration and cooperation. Building upon the experience gained from international space missions and the International Space Station, ISS collaborative efforts can accelerate progress and leverage expertise from different countries and space agencies. Shared research, knowledge exchange, and joint ventures can contribute to more sustainable solutions and advance the overall success of Martian colonization. By addressing these challenges and focusing on sustainable infrastructure development, Mars can become a self-sustaining and thriving environment for human habitation. The journey toward the long-term future of Mars colonization requires continuous innovation, scientific breakthroughs, and a collective commitment to exploring and expanding our presence beyond Earth. Conclusion. Terraforming Mars is a complex and ambitious endeavor that requires a deep understanding of planetary science, innovative technologies, and careful ecological management. While the process presents significant challenges, such as creating a suitable atmosphere, establishing a self-sustaining biosphere, and ensuring long-term stability, it also offers the possibility of transforming Mars into a habitable world for future human colonization. By harnessing the power of lasers, leveraging existing resources, and implementing advanced techniques, we can take a significant step towards realizing our future as an interplanetary species. Through continuous research and collaboration, we can expand our knowledge and capabilities, ultimately paving the way for humanity's expansion into the stars.